So we're going to label this as the structure of the alpha helix. Now I'm going to show you this is a kind of corkscrew first. And then in orange, I'm going to show individual amino acids. 1, 2, 3, 4, 5, 6, 7. 1 to 4. So that's coming around a little bit. Now, what I want you to be able to envision is to think about this as an amino acid. Now then, imagine these amino acids as steps on the spiral staircase. So imagine going up a spiral staircase. As you go up a spiral staircase, you take small steps. I think it takes 12 to 14 to go around a full circle. Here what we find is that if we face this direction and we start up the spiral staircase, walking up the spiral staircase, we will go a full 360 degrees every 3.6 amino acids. What we're saying is that each amino acid goes around the curve by 100 degrees. Now remember, to make a full circle requires 360 degrees. So if I'm facing this way and I'm walking up the steps, it's 360 degrees by the time I get back facing the same direction again. Now I've gone up several steps, but I'll be facing the same direction again. And that's true here as well. For each step, you move around the circle by 100 degrees. That means it takes 3.6 amino acids, 1, 2, 3, and then to the fourth, to go a full circle. What we're going to see is that the nitrogen here on this amino acid will hydrogen bond with its hydrogen to the double bonded oxygen on this amino acid. So 1 goes to 4, 2 goes to 5. 1 plus 3 is 4. 2 plus 3 is 5. 3 goes to 6. Now, so in other words, if you look at it again, imagine walking up the spiral staircase. But now, rather than having 12 or 14 steps to go around a full circle, we're going to go around the full circle in 3.6 steps. Those are mighty big steps. But each time we take a step, we turn 100 degrees. So if we're facing this way, 90 degrees is here, 100 degrees is here. So basically, when I step from the first amino acid to the next amino acid, I'm going to turn this far. And when I step to the next amino acid, I'm going to now turn another 100 degrees. So by the time I walk up 3.6 amino acids, I've turned a full 360 degrees. By the time I get to this fourth amino acid, I've gone a little bit farther than 360 degrees. The orientation of this is that if we would simply take the amino acid sequence and place the nitrogens above one another so that they were evenly stacked, we couldn't form this hydrogen bonding. So what we do is we have to offset them a little bit. And the offset allows us then to go 1 to 4, 2 to 6, 3 to 7. So that each amino acid is hydrogen bonded with 3 amino acids down the steps below. And in that way now, we can hold this structure stable by using the hydrogen bonding. What's more is the hydrogen bonding between these amino acids, every fourth amino acid, now throws the amino acid sequence into to this helical structure. It becomes a spiral staircase because of the bonding between this amine hydrogen and this carbonyl oxygen. So this holds it together and stable, but what's more, because of the flexibility of the string of amino acids, it spins the sequence of amino acids around a central imaginary pole. The other thing I want to say here, and we'll come back to it, is that this step from one amino acid to the next, again, imagine you're walking up a spiral staircase. As you walk up the spiral staircase and you climb higher, each amino acid step moves by 0.45 nanometers. These are really, really small steps. So we'll come back to this when we begin thinking about how we're going to thread an amino acid sequence across a phospholipid bilayer, remembering the phospholipid bilayer is 6 to 7 nanometers wide. You can see how many it's going to take to get across. So any questions up to here? You really have to spend some time struggling with this, wrestling with this, to get a sense of how you can walk up a spiral staircase one amino acid at a time, and how the amino acids are being held together every fourth amino acid, 1 plus 3, by these hydrogen bonds. But the other form of structure that we see here is the so-called beta-pleated sheet. And I'll draw this crudely first, and then I'll show you a more accurate depiction of it when we look at a slide. The beta-pleated sheet, the amino acid sequence, the beta-pleated sheet is thrown into these sort of zigzag patterns. And then someplace out here there's a kink, and then we get the zigzag pattern back again. And it's at these peaks where we begin to see an oxygen to a hydrogen bonding. So in between these two extremes of the beta-pleated sheet and the alpha helix, let's draw a protein which will start out here at the amino terminus. We're going to run a region of alpha helix. And then we'll have a region of beta-pleated sheet. This may now have a kink in it. We have a beta-pleated sheet. We can now run a sequence of amino acids. Here's our beta-pleated sheet. We can run some more alpha helix, and down here another beta-pleated sheet, down to the carboxylic end. You'll often see this kind of representation of proteins where it will show a sequence, a region of alpha helix, a region of beta-pleated sheet, a region of alpha helix. And this now is the beginnings of the structure of the protein. We're now beginning to incorporate alpha helical regions and beta-pleated sheet regions into the structure of the protein. But again, this is just secondary structure. This is all dependent upon hydrogen bonding between carbonyl oxygens and positively charged hydrogens on the amines. No more structure in the amino acids is required. We do not need R groups for any of this structure. This is all based on hydrogen bonding within the molecule, as we saw with the alpha helix, or between strands with the beta-pleated sheet. But of course, this really isn't enough to generate the full three-dimensional structure of a protein. To understand the full three-dimensional so-called tertiary structure of the protein requires another level of understanding. The next level of understanding is to go beyond the hydrogen bonding within the molecule or between strands of the same molecule, and now begin thinking about the role of the R groups. So that's where we're headed now, is to try to now incorporate the R groups into thinking about the full-fledged three-dimensional structure of a protein.